Welcome to this technical summary of the paper titled Snap, Crackle, and Pop. This is why the potential of mean force clashes with the. Today, we will explore the complex interactions and challenges involved in understanding the potential of mean force in molecular systems, using detailed molecular dynamics simulations. This paper addresses the fundamental question: why does the potential of mean force, a widely used effective description in molecular and statistical physics, sometimes fail or clash with the underlying microscopic dynamics? Understanding this disconnect is crucial because the potential of mean force is often employed to simplify the many-body problem into a one-dimensional effective description, which is easier to analyze and simulate. However, discrepancies between this approach and actual molecular dynamics have significant implications for modeling complex systems accurately, impacting fields such as material science, chemistry, and biophysics. The authors tackle this problem using simulations of Lennard-Jones particles confined vertically under gravity in a cuboid simulation box. They employ advanced molecular dynamics techniques combined with detailed analytical calculations, including the evaluation of force fluctuations and memory kernels. By analyzing the dynamics and statistical properties of particles under these controlled conditions, the study aims to shed light on the microscopic origins of the inconsistencies observed in the potential of mean force framework. This high-level approach thus links rigorous simulation with theoretical insights to clarify where and why typical coarse-grained models may fall short, especially concerning noise and memory effects that are often oversimplified. Figure 1 provides a snapshot of the simulated system under study. It illustrates 500 identical Lennard-Jones particles confined in a cuboid box, exposed to a gravitational force. Each particle interacts via Lennard-Jones potentials, characterized by parameters sigma for particle diameter and epsilon for interaction energy, and each carries a mass m. The simulation box has dimensions 10 times sigma by 10 times sigma horizontally and 20 times sigma vertically. The system's boundary conditions are periodic in the horizontal x and y directions, while the vertical z direction features Lennard-Jones walls acting as confining boundaries. Additionally, a constant force field, modeling gravity, acts in the vertical direction. This setup enables the authors to study how the particles distribute and behave under gravity, ensuring a controlled, realistic environment to probe the potential of mean force and its associated dynamics. Through this configuration, the authors can access all necessary quantities from equation 18 for their theoretical and simulation analysis. The snapshot conveys the spatial arrangement of particles, providing a visual context for the ensuing statistical and dynamical analyses. Moving to Figure 2, the authors present key results from the molecular dynamics simulations of the Lennard-Jones particles confined vertically under gravity. The figure is composed of 3 panels. Panel A shows the potential of mean force, WMF of z, derived from the equilibrium position histograms of the particles along the vertical axis. 2 vertical lines mark a particular region used for further analysis of residence times, focusing on the interesting dynamics in that spatial window. The potential is obtained by umbrella sampling to improve boundary statistics, and then numerically differentiated with a Savitsky-Golay filter to determine the mean force, FMF, of z. Panel B displays the variance of the fluctuating force as a function of time, including a light gray error band representing the standard deviation of the mean. This shows explicitly that the variance is time-dependent, indicating that the fluctuating forces cannot simply be modeled as white noise with time-independent statistical properties. The variance plateaus at around 1 Lennard-Jones characteristic time, tau Lj. Panel C contrasts the autocorrelation function of the fluctuating force in the stationary limit with the memory kernel multiplied by the variance of the momentum along z. Crucially, these two functions do not coincide, meaning the fluctuation-dissipation relation, or FKR2FDT, is not fulfilled even at late times. Attempts to reconcile them by rescaling fail as the positions of the minima differ. This indicates that the noise is non-trivial and cannot be captured by standard coarse-grain models with simple noise terms. Altogether, this figure supports the author's interpretation that reproducing the correct coarse-grain dynamics requires a more sophisticated modeling of noise and memory effects in the potential of mean force framework. Figure 3 compares the distribution of residence times within the region marked by the 2 vertical lines in Figure 2a for 2 different types of simulations. The first distribution corresponds to the original molecular dynamics simulations, while the second is obtained from coarse-grained simulations using the auxiliary variables method. This method implements a noise term designed to satisfy the fluctuation dissipation theorem at all times and aims to reproduce the dynamics captured by the detailed MD simulations, but at a reduced computational cost. The figure highlights a clear deviation between the two distributions, revealing that integrating the coarse-grained equations with a noise term that strictly obeys the classical 2FDT does not capture core dynamical properties of the original system. Specifically, the residence time distributions differ noticeably, implying that the simplified noise model ignores subtleties of the fluctuating force dynamics. This emphasizes the author's interpretation that standard coarse-graining approaches may underestimate or misrepresent critical memory and noise effects. Hence, this figure substantiates the core message of the paper. Modeling the fluctuating forces in systems with complex microscopic interactions requires more nuanced approaches beyond simple noise that fully satisfy the fluctuation-dissipation relation at all times. In conclusion, this study highlights important challenges in the coarse graining of molecular systems via the potential of mean force framework. By simulating a system of Lennard-Jones particles confined under gravity, the authors demonstrate that the fluctuating forces acting on particles have time-dependent variances and autocorrelations that do not fulfill the classical fluctuation-dissipation relation. This indicates the presence of memory effects that cannot be captured by simple noise models with time-independent statistics. Furthermore, coarse-grained simulations that employ noise terms strictly satisfying the fluctuation-dissipation theorem failed to reproduce key dynamical properties, such as the residence time distributions observed in full molecular dynamics simulations. These results underscore the necessity for more sophisticated modeling of memory kernels and noise in effective descriptions, especially in complex non-equilibrium and confined systems. The insights provided here pave the way for improved theoretical and computational approaches capable of bridging the gap between microscopic dynamics and coarse-grained representations, ultimately enhancing the accuracy and predictive power of models in molecular physics and related fields.